What's up, everybody? This is a video designed to help you with your introduction to rotational kinematics. You've already done this before. We're just going to introduce some new terms and new variables that you got to get used to. Otherwise, you already have the skills to handle this. You just got to understand what these terms mean. So let's get to it. We're going to start with a circle here, and you can see it has a radius r, and there's a little red dot. And that red dot is where you are. And we are going to travel a distance from here to about here. That is your delta S. That's known as arc length. Maybe you've done it in math class. Arc length. Okay. It's also known as your linear. My pen's not writing. Linear or translational distance. Basically, distance traveled. Don't overcomplicate it. Okay. Now, during that time, you've also kind of swept out an angle. That angle is right here. You've gone some delta theta. Okay, there's been a change in angle. This delta theta is known as, sorry, my pen's like acting stupid. Delta theta is angular displacement. Angular displacement. And great news, people. It's measured in radians. Yep, that's right, radians. Okay, well, we'll talk a little bit more about radians. But good news is your calculator is still in degrees. So that helps. All right, so we've gone from one point to another. We've traveled some arc length or an actual distance. And during that time, as we've gone around, we have gone through some angular displacement known as delta theta. All right, let's get to a little derivation time. It's exciting. All right, so it took some time for us to do this change in angular position, this angular displacement over angular time, like literally displacement over time. You know what that is? That's like a velocity. And for us, it's Greek letter omega. It's kind of like a lowercase w. And it's angular velocity. Angular. That's how I spell angular in my world. Angular velocity. And if you just see this, like this expression here, this would be actually constant or average angular velocity, because there's no acceleration, so average. Angular velocity. Well, if you look at the units, delta theta is measured in radians, time's measured in seconds, so this is radians per second. Okay, so a radian. I mean, what is a radian? Here's the way I'm going to think about it, and I'll probably mention this in class. Radians for me, if I hear 6 radians, that's roughly 2 pi. That's like one whole revolution. So if I'm hearing something like, for example, 12 radians per second, in my mind, I'm like, that's roughly 2 rotations per second, because that little red dot here will travel around twice, basically 12 pi radians in a second. So going around about 2 times per second. Okay, let's keep deriving. What if there's a change in angular velocity? What if we have like a delta omega? And hopefully if you heard the word change in velocity, you know what's coming. Okay, so change in angular velocity over time is alpha. Alpha is angular. How do you spell angular? Angular acceleration. All right. My pen's not working, and it's annoying. All right, angular acceleration. And, well, just like your other acceleration, it's going to be, if omega is radians per second, and we're dividing by seconds. Now we have radians per second squared. Terrific. Let's keep deriving some math. Here we go. So now we're getting to the real stuff. Let's take this and kind of expand it out. You ready? Delta omega is omega final minus omega initial. If I move the time over, I get equals alpha delta t. And if I add over the omega initial, I get final angular velocity is equal to initial angular velocity plus acceleration times time. Does that sound familiar to you? If it doesn't, we need to talk. Yeah. This is basically final velocity equals initial velocity plus acceleration times time. No big deal. Without going through all the other derivations, you could probably guess. Like we had, so just so you could see it, we had old school. Come on, right? VF equals VI plus AT, right? They kind of look familiar. The next one we learned was delta x is initial velocity times time plus 1/2 acceleration times time squared. And the equivalent angular version or rotational version will be, so distance is kind of like delta theta. That's an angular distance, if you will. We have initial velocity, so that's omega initial times time, plus 1/2 acceleration. Our new acceleration is alpha. Careful when you write the 1/2 and the alpha. Sometimes people mess that up and cancel them out somehow. Like they look like alpha over alpha. Delta t squared. And the final one we learned was the VF squared equation. Final velocity squared equals initial velocity squared plus 2a delta x. Distance delta x. The equivalent in terms of rotation is, hopefully you can guess, omega final squared. So it's final angular velocity squared equals initial angular velocity squared plus twice the acceleration, alpha, times distance, which angularly or rotationally, angularly, is that a word? Or rotationally is delta theta. So you've seen this before, okay? All right. These are the new expressions. These are on your AP equation sheet. You just need to familiarize yourself. I'm not editing this. Familiarize yourself with the variables and what they mean, but you already have like kind of this to fall back on. You know what it is. Speaking of this, we need to make some connections between these two things. Okay. Above, we had that delta theta equals delta S over R. Whoa, hey now, what's that about? Delta S over R. So we've got delta theta equals delta S over R. I'm going to rearrange that, and what we get is, if my pen would write, delta S is equal to R delta theta. This is what relates your linear distance, delta S. So this relates linear distance. You might hear the word linear. You may hear the word translational. Translational distance to an angular distance. Or angular displacement, excuse me. Angular displacement. I hope you're watching this at 1.5 because, man, watching me write, it's got to be boring. Okay. Well, let's keep going with this. If we do delta S over R delta theta, so this distance traveled occurs over some time, and your angular displacement occurs over some time. And if you look at this, it's, hey, distance over time, that sounds like velocity. And delta theta over delta t, I thought we said that was angular velocity. So this is R omega. This relates your translational or like just regular old velocity that we used to study to your angular. Okay. And check this out. This is going to be amazing. So if I have a change in velocity over time, a delta V over delta T, and I have a delta omega over delta T, you know what we get? We get acceleration, our translational. Translational, just when you're translating, you're moving in a 1D direction. You're moving forward or backwards or up or down, but you're moving in 1D, like the old school acceleration we used to do, equals R alpha, because delta omega over delta T is alpha. These things here, delta S equals R delta theta, V equals R omega, and A equals R alpha are on your equation sheet, but they're what connect your angular stuff that we have over here to your linear / translational stuff you've been doing all year, okay? These are known as, this one's often known as Romega, R omega, Romega. This one's known as Ralpha. If you're daring, you can call the one above, this one like right here, you can call it Rotheta, Rata, I don't know, but they're easy to remember. You'll hear me say Ralpha and Romega all the time. Okay, so these are new expressions and we got to get used to using them. Let's get after it. This is one of the examples that we were going to do in class. Okay. Well, I see stuff about a diameter of a wheel, rotating in RPMs. Okay, I got a time in there. It says stop. What is the angular acceleration of the wheels? Okay, do you remember back in the day, we used to do, I don't know, we used to list our variables. Let's do it. So I'm going to list them. Omega, if my pen writes, omega initial, omega final, alpha, delta theta, delta t. Okay. Initially, we're spinning at 200 RPM. That sounds interesting. That's 200 revolutions per minute. I need to convert that because I need to get to radians per second. So this would be times, this is factor label, or as the chemistry people call, dimensional analysis. That's 1 minute is 60 seconds, and then there's 2 pi radians for every 1 revolution. So revs go, minutes go, and 2 pi radians, I end up with 20.9 radians per second. So again, what does this mean to me? If I divide by 6, it's roughly 3.5. So this thing is rotating roughly 3.5 times per second. That's how I see it, just mental math. Otherwise, radians are scary. Don't tell the math teachers I said so. You do come to a stop, so your final velocity would be 0 radians per second in a time of 6 seconds. And we're looking for angular acceleration. So this is like the old school stuff that we used to do. It's not a big deal. Find the expression that works and sub in. Like that's it. It's omega final, initial velocity plus acceleration times time. And this goes to 0. So we get 0 equals 20.9 radians per second plus alpha times time, which is 6 seconds. And you'll end up with alpha is negative 3.48 radians per second squared. I did that in my head in no time. What's up? Then it asks, how far do you go during this time? Ooh, how far? That's a linear distance. Interesting. Okay. Well, distance, angular distance is delta theta. So maybe since I have all this angular stuff, I'm going to get delta theta because that might help me. So I'm going to use the expression I choose to, which is delta theta is initial velocity. Oh, wow, look what I did. Initial velocity times time plus 1/2 acceleration times time squared. So I'm going to solve for delta theta. It's 20.9 radians per second. That's our initial angular velocity. Time is 6 seconds plus 1/2 the alpha we just got, which was negative 3.48 radians per second squared times 6 seconds squared. Isn't this fun? I don't know, depending on your definition of fun. Delta theta is therefore 62.8 radians. Okay. How far did we go? Well, far is a linear distance. Okay, so we got to figure out how far did we go in terms of a linear distance. Hey, we got that cool equation. I believe it's called delta S equals rata or theta or whatever you want to call it. But you need to know this one. I think it's on the equation sheet. Don't quote me. So delta S, I think they said the diameter of the wheel was 0.7 meters. So our radius is 0.35 meters. Angular displacement was 62.8 radians. And when we put these together, we get that the bike, or a point on the edge of the wheel, travels 22 meters. And if a point on the edge of the wheel goes 22 meters, guess what? So does the bike. Side note, you may be asked how many rotations or revolutions this is. And if that comes up, you gotta convert. So if I do this, I have 60, oh my goodness. Come on, you can write 62.8 radians. How many revolutions is that? For every one revolution, it's 2 pi radians. So basically, you're just dividing by 2 pi. And as it turns out, you get exactly 10 revs. You get 10 rotations. It won't let me write 10 revolutions. Yay. Okay. So that wasn't so bad. All we did was list variables and solve. We were asked for a linear distance, so we used our connector equation, the rata or theta, to get an angular displacement into a linear or translational displacement. All right, let's do another one because we're 16 minutes in and you're probably bored as hell. Okay, this one's a quick one. We got a discus thrower accelerating at a certain rate rotationally, and they have a radius of 0.8 and they rotate 2.5 times and they release the disc. What is the angular velocity when it's released? Ooh, boy. Sounds scary. All right, so old school, initial velocity, final velocity, acceleration, angular displacement, and time. List your variables. List them vertically. Why not? That's what we used to do. I'm assuming, because it never mentions initial velocity, and if it doesn't ask us to solve for it, that most discus throwers start from rest. Final velocity, that's what we're looking for. Angular acceleration is 50 radians per second squared. We rotate 2.5 times. Okay. 2.5 rotations times 2 pi radians for every rotation gives us, I know some of you are probably like, 5 pi. I don't like you. I know that's more exact, but I'm going with 15.7 radians. I know it's going to bother some people. And now we're looking for omega final. Okay. We can do, let's do it up here. Well, we don't know time. What's that equation that doesn't have time? Wasn't it the VF squared? But now it's the omega F squared plus 2 alpha delta theta. So omega final is going to be the square root of 2 times 50 radians per second squared times an angular displacement of what some people may call 5 pi, but I'm writing as 15.7 radians. Deal with it. So omega F is going to be 39.7 radians per second. Okay, that wasn't so bad. What's question B? If released at an angle of 40 degrees and 1.8 meters above the ground, how far will it... Dude, who put a projectile problem here? It's okay, but we need a velocity. I don't know how fast it's going. How fast is it going? I don't know. I have that it's 39.7, which is roughly six revolutions per second. Wow, he's really spinning because I'm dividing by roughly 6. So he's doing, or she is doing 6 revolutions per second. That's fast. Okay. But if we want to do a projectile, we got to convert that to a velocity. Luckily, we know this thing, rhomega. V equals rhomega. Sorry, I'm okay. This video is getting long and I'm getting punchy. All right, well, V, there we go. It's not letting me write. There we go. Equals R, which is 0.8 meters, 39.7 radians per second. And some of you may be saying, like, hey, wait a second. What happens to units? Is it meter radians per second? No. Radians are actually a unitless thing. So it's just meters per second. That's all it is. and it's roughly like, I don't know, 31. Oh my goodness, it's just not letting me write. 31.8 meters per second. Hey, now that we know that, you know what we can do? An angled projectile where we did 31.8 meters per second, cosine of whatever, and I'm not going to put you through this, but cosine of 40, that would be your Vx, 31.8 meters per second. Sine 40, that would be your Vy or Viy, and then you could do an old school projectile problem, because that's fun. So that's how we connect the rotational to the translational. Okay. By the way, there is a homework problem real quick. Here's another one. If I'm going to draw an FBD of this person doing this ride is the one where you're pinned up against the wall. You've got the normal toward the center. FN. This pen is just terrible. You got FG, FG, and you've got FF up. Yes, you do, so you don't slide down the wall. So we know that mu Fn is going to equal mg. That's our sum of the forces in the y, which is going to be 0. Okay, but in the quote x, it's actually circular motion. Everybody's favorite, sum of Fc equals MAC. So you've got Fn equals mv squared over r. Now this is your translational or linear velocity. So as we're going to inevitably sub this in here, we would solve for v, and then once we have v, we can make that an omega, and then once we have omega, we could do some angular questions. All right, let's wrap this puppy up. You've suffered for so long, and I'm really sorry about this. Strategies. List your variables like you used to do, okay? You don't get much time to get used to this, but you need to get used to the new variables, but you have these skills. In green, we have our connectors between our rotational kinematics and our old school linear or translational kinematics. Should there be a multi-part problem, just like old school, final angular velocity of one part becomes the initial angular velocity of the next part. You can add the times to get the total times. You can add the angular displacements to get the total angular displacements. We can convert those into a linear distance using rata. And then RPMs, you're going to see that a few times. It's just unit conversion. I usually write revolutions per 60 seconds right away, however many there are. And then it's always 2 pi. So you're basically multiplying by 2 pi and divided by 60. If you memorize that, I'm fine with it, but I have never even thought to do that. I just write out the dimensional analysis. Anyway, it has been a long time since I've made a new video. This is now 2026. And I noticed that there was no kinematics video. And I still think I have not improved my skills after all this time. So the best I'm going to do is give this puppy 3 out of 5 stars. Hope it was helpful.